The transesterification reactions we examined in section 22.1 are rather limited in scope, involving an ester as the carboxylic acid derivative and an RO- as a nucleophile. And the reason they're pretty limited is because you're taking an ester and converting it to another ester. And sometimes we need other functional groups for reactivity. So there are numerous other acyl substitutions that can be carried out simply by using different combinations of carboxylic acid derivatives and nucleophiles. And equation 22.4 shown here is an example of that. And so what we're seeing here is that CH3O- can displace chlorine from an acid chloride like benzyl chloride to produce an ester. So we go from an acyl chloride to an ester. And so now we have a new functional group. So let's look at the mechanism for how this occurs. When we look at this, we're going to draw our starting materials. Now remember, you always need to redraw these when you're showing the mechanism. And we are going to draw our reactant. And remember, lithium is a spectator ion. And these electrons are going to come and they're going to attack that carbonyl carbon because it's partially positive. And we remember that electrons are attracted to things that are positive or partially positive. And then these electrons are going to go up on that oxygen. Now, this is a nucleophilic addition. All right, and we have created a tetrahedral intermediate. All right, now this tetrahedral intermediate will undergo a tetrahedral collapse with the chlorine as the leaving group. And of course, chlorine is pretty stable. It can accommodate that negative charge really well. And so now, that of course is a nucleophile elimination. Some older books use nucleophilic elimination, and that's how I learned it. So sometimes you'll hear me use that interchangeably, but I just want you to be, so I want you to be aware of that. And here's our product. Okay. This is just a normal, like the same steps as before. Nucleophilic addition, nucleophilic elimination, we have our product. Now, here's the thing. Not every combination of an acid derivative and nucleophile leads to an effective acyl substitution reaction. So I want us to look at some examples. So let's look here. Here's 22.6. And this shows that essentially no acyl substitution takes place when an ester is treated with a chloride ion. Now, we understand this by examining the generic acyl substitution reaction shown here in 22.7. Notice that the nucleophile, which is shown here, bears a negative charge on the reactant side, and the leaving group bears a negative charge on the product side. If the leaving group is more stable than the nucleophile, right? And this is reflected by the weaker basicity of the leaving group. Then the reaction is energetically favored and generally occurs readily. Now, if the nucleophile is more stable, then L-, then the reaction is energetically unfavorable. And does not proceed readily. Okay, and so this is the case, and what we're seeing there is the case up here, right? In this case, where the nucleophile is Cl minus, and the leaving group there is OCH3. Okay, so what's happening here is Cl minus is a lot more stable than OCH3. So there's no reason for it to react. Now, is there a way for us to predict this? And the answer is yes. We use a stability ladder. This stability ladder is incredibly helpful. And so basically, when we look at this, think about a ladder. It's generally... Okay, sorry, there was a weird noise. Think about a ladder. It's generally easier to go down a ladder than to go up a ladder, right? And so with these arranged like this, the acyl chlorides are the most reactive. They'll react with any of these, okay? But this carboxylate ion here is the least reactive, right? And won't react with any of these up here. So we can kind of sum this up by saying an acyl substitution that converts an acid derivative from a higher rung on the stability ladder to one on a lower rung is energetically favorable, right? And an acyl substitution that converts an acid derivative from a lower rung on the stability ladder to one on a higher rung is energetically unfavorable. Okay, and so what this means then is that an acyl chloride can react with this and turn into an acid anhydride. An acyl chloride can react with either this or this and turn into an ester or carboxylic acid. An acyl chloride can react with this and turn into an amide. But look, the acid anhydride can react with these to turn into this. They can react with this to turn into this, and so on. But an acid anhydride is not going to react with a chlorine to turn into an acid chloride. We're not going to be able to go up. Okay, we can only go down. Okay, and so let's do an example. Okay, so which will the reaction here take place? If it will, draw the complete detailed mechanism and predict the major products. Okay, well, so when we look at this, we need to ask ourselves some questions. So when I solve a problem like this, I think, okay, what is the nucleophile and what is the leaving group. So the nucleophile here is this right here. So it's CH3CO2 minus. Okay, that's our nucleophile. And it's going to attack the carbonyl carbon in a nucleophilic addition step to produce the tetrahedral intermediate. And so the chlorine here is going to be our leaving group. And so the leaving group there is going to be Cl minus. Okay. And so which side of the acyl substitution is favored by charge stability? And so this is kind of the next question I asked myself. And just honestly, the Cl minus, right, can better handle a negative charge than the oxygen. It's more electronegative. All right, it's also larger. Okay, so it can better handle that negative charge than the oxygen. So charge stability here favors the product side. Okay. Does the acyl substitution represent going up or down the stability ladder? So the acid derivative on the reactant side is an acyl chloride. So we've got an acyl chloride here. And on the product side, this would make an acid anhydride. Okay. And so this represents going down one rung of the stability ladder, and this would be energetically favorable. So it'd be going down, and it would be energetically favorable. And so when we look at this to produce our product, right, and practice the mechanism here, we follow those same steps that we've done before. We're going to attack here. Those electrons are going to go there. Now we're going to go through a tetrahedral collapse, where chlorine is going to be our leaving group. And there we are. And so that's our product. So let's look at some other reactions. And let's look at the one that I talked about on the very first slide, which is saponification. So a hydroxide, which is an OH minus, and an alkoxide, which is an RO minus, these ions generally have similar nucleophile strengths and leaving group abilities. So you might expect that a carboxylic acid would react with an alkoxide ion to produce an ester. If such a reaction would take place, that RO minus would replace the HO minus, much like we saw with transesterifications, where one alkoxide ion replaces another. However, what we see is not that. Instead, the alkoxide anion, which is a strong base, so this guy right here is a strong base, right, deprotonates the carboxylic acid rapidly. This is a rapid reaction, and irreversibly, right, to produce a carboxylate anion, and after that, there is no further reaction. Okay, and so no further reaction takes place because carboxylate anions are at the very bottom of the stability ladder. So these guys are at the very bottom of the stability ladder. Okay. So any acyl substitution reaction that converts a carboxylic anion to another carboxylic acid derivative in the stability ladder would be highly unfavorable. So these carboxylate anions are reactive in large part because they have equivalent resonance structures, resulting in electron delocalization that heavily stabilizes the carbonyl group's pi electrons. Okay, so these carboxylic anions are unreactive because they have equivalent resonance structures and the resulting electron delocalization heavily stabilizes the C double on group's pi electrons. Okay, and so that's what we see. So we've got, and that's shown there in the black arrows, is that resonance stability. And then what furthermore, right? So that was mostly with A here, but here with B, we have these carboxylate anions are negatively charged, right? And so because we have this negative charge, they repel incoming nucleophiles. So the carboxylate anions are negatively charged, right? So they repel incoming nucleophiles, okay? And so that's why they are unreactive. So although the deprotonation of a carboxylic acid prevents conversion of a carboxylic acid to an ester under basic conditions, this kind of deprotonation promotes the conversion of an ester to a carboxylic acid. So let's look at that, right? If ethyl acetate, which is shown here, which is also known as ethyl ethanoate, is treated with potassium hydroxide, or really any base, followed by an acid workup, an ethanoic acid or acetic acid is produced in a relatively high yield. The first reaction in this sequence is known as the saponification reaction, which literally means soap making. Sapo is the Latin root for soap. Ancient civilizations made crude soap by boiling animal fat, which is chiefly kind of like these long chain esters, with wood ash as that source of hydroxide ions. The carboxylic acid's produced when the ester undergoes the saponification followed by the acid workup. So what we see here, of course, is going from an ester to a carboxylic acid. Another thing that I want to point out here, that ethyl acetate is a common organic solvent used in liquid chromatography. It's also used in as a decaffeinating agent for coffee because it can pretty efficiently extract caffeine from the bean without excessively removing other compounds that would change the flavor of the coffee. So that's kind of interesting. So decaffeinated coffee is chemically decaffeinated, and they do that by using ethyl acetate. So I'm sure the burning question in your heart is, well, what's the mechanism? How does this work? And I'm so glad you asked because we are going to do the mechanism next. So let's draw our reactants. All right. And the first thing we're going to see is a nucleophilic addition. Okay, where this OH is going to come in here and attack right there, and then those electrons are going to pop back up there. Okay? And so we have formed our tetrahedral intermediate here. Okay, and now we're going to have a nucleophilic elimination reaction, which is our tetrahedral collapse. And your book calls it a nucleophile elimination, so I'm trying to change what I say. Right? These electrons are going to go down here, and then this group is going to leave. Okay? Now, when that happens, these electrons are going to come in and they're going to steal that proton, and those electrons are going to go onto the oxygen. And now we have a proton transfer, right? And then what we see here and I want to point out, because you're going to see something that's weird, okay? And I should have pointed out here. This is an irreversible deprotonation, okay? And the reaction stops there. And so what happens then is now over here, you do an acid workup, and it replenishes that hydrogen there. So from the acid workup, you end up with an H+, and there's another proton transfer reaction. Mechanisms, I know it seems weird to do a proton transfer and then another proton transfer, basically getting to the same thing. But you need to remember, mechanisms represent what we know is happening in the reaction. And so at the end of this reaction, there's an irreversible deprotonation, and you have to do the acid workup to protonate that as a carboxylic acid. So the fact that this is irreversible helps drive the reaction to completion. Okay? And so that's one of the driving forces here. So to kind of better understand this, we are going to look at the free energy diagram. So here's the free energy diagram. Notice that the products of the nucleophilic addition elimination, the carboxylic acid and the alkoxide anion, appear at roughly the same energy as the overall reactants, right? So these guys here appear at roughly the same energy here. This is consistent with esters and carboxylic acids appearing on the same rung of the stability ladder, right? And so this is something that we would expect. But that next deprotonation to here, right, rapidly converts a carboxylic acid into a carboxylate anion, which represents going down 2 rungs of the stability ladder. Right? And that's a very energetically favorable process. So it's then the subsequent acid workup where we add the proton back to get the carboxylic acid. All right, so that concludes our discussion of a saponification reaction. In the next screencast, we're going to talk about carboxylic acids from amides and the Gabriel synthesis of primary amines.